All right, hello and welcome back. So this is a requested video. So this is a problem that was emailed to me, and it's a great problem. So I'm happy to take a look at it. Happy to make a video for it. And if if you have a video that you want me to make, if you've got a problem or something, feel free to email it to me. I'll take a look at it, and depending on my schedule, I'll make it sort of as soon as I can. But let's go ahead and do this one. So this is a great empirical formula problem. It's definitely very challenging. It's one of the hardest empirical formula problems sort of that I've seen. But there is sort of this weird aspect where they're giving us the molecular weight, and we can actually, there's sort of like a shortcut method to sort of solve for the molecular formula and the empirical formula using that molecular weight. I'm not going to do that in this video, because we're not always going to be given a molecular weight when we're asked to find empirical formulas. And if you sort of use the shortcut method, then you're not going to be able to solve the empirical formula if you're not given that. So I'm actually going to ignore the molecular weight for now. We're gonna pick it back up at the very end of the video to find the molecular formula. But I'm going to go through this step-by-step process, sort of, I think, how the author of this problem probably intended it to be solved, but I do recognize that there's a shortcut method that some of you might want to talk about or do, but I'm not going to be talking about that in this video. I'm gonna go through the whole process. Maybe I'll talk about it at the end. Okay, so let's go and get started. So the first thing that I'm going to do is just sort of organize the information that's given. The first thing that I see is 13.66 milligrams of the compound is produced. 13.66 milligrams of a compound produces 10.71 milligrams of carbon dioxide and 3.28 milligrams of water. And in the original problem that was sent, this was actually typo. So in the original problem, it said 3.28 grams, but in parentheses here, I've added milligrams. I analyzed this problem basically, and I'm 100% sure that this is supposed to be milligrams. It doesn't make a lot of sense for it to be grams, because we're taking 13.66 milligrams and producing, right, from that we're going to get 10.71 milligrams and 3.21 milligrams of water. So it doesn't really make sense that would be grams. So that definitely was a typo in the original one. Another 4.86 grams of the same compound yielded 3.46 grams of bromine. So right there I can see that we can get a mass percent for bromine in our compound just because we're told how much bromine is produced there. And it's pure bromine. The molecular weight, I said we're going to ignore that for now. Calculate the mass percentages of carbon, hydrogen, bromine, and oxygen. Determine the empirical formula. So let's go ahead and get started. The first thing that I would do, like I said, I'm gonna do it based off this mass percent. I like converting everything into grams. It's not necessary, especially for this problem since we're using mass percents, but I just think it's a good practice. So I'm going to do that. CHBRO, and I'm just going to write CHBRO. Maybe we'll put it in quotes because it's not one carbon, one hydrogen, one bromine. I'm just using that as a shorthand notation. That's going to form 0.01071 grams of CO2. And then I'm going to calculate the mass percent of carbon in CO2. So that's going to equal 12.01 over the mass of CO2, which would be 44.01 times 100, and that equals 27.3%. So what this is telling me, this calculation is telling me, is that the mass percent of this 0.01071 grams of CO2, 27.3% of it by mass is made of carbon. So from this I can say, well, how much carbon, just pure carbon, am I going to have from this CO2, which I can then relate back to my original sample. So if this is my grams of CO2, then that means I'm going to end up with 0.002923 grams of just pure carbon. So that's taking 0.273 times this value here. So from this sample of CO2, 0.00293 grams of it, that's how much 2923 grams of carbon, that's how much carbon is in that sample. And that carbon came from this original sample up here. We'll do the same thing for our hydrogen, 0.00328 grams of H2O. I'm going to find the mass percent of hydrogen in H2O. That's just 2.02 divided by 18 should be 11.2%. So again, from this 0.00328 grams of water, if 11.2% of it is made up of hydrogen, then I could solve for how much hydrogen, 0.000368 grams of pure hydrogen. So that's how many, in this sample up here, that's how many grams of hydrogen there were, that's how many grams of carbon there were from my sample. So now we actually have the data that we need to solve for the mass percent of carbon in my CHBRO. And that's going to equal this number here, 0.002923 grams of carbon, divided by the mass of my entire sample, 0.01366 grams, times 100 equals 21.4% carbon. So my sample, to find this mass percent of carbon in my sample, I need the mass of carbon divided by the total mass. This is my total mass, right, for this experiment that I'm doing. I've figured out how much, what my mass percent of carbon is, so I just take my mass of carbon divided by my total mass. That gives me my mass percent of carbon in that CHBRO sample. We'll do the same thing for hydrogen. Mass percent of hydrogen in CHBRO. Do a similar calculation. I'm not going to show that, but that should be 2.7 or 2.69% hydrogen. So again, just taking this value here divided by our total mass of CHBRO from our sample gives us 2.7% hydrogen. Now for the oxygen, we actually can't figure out the oxygen yet. And the reason for that is that the oxygen that forms in the CO2 and this H2O, that's actually coming from oxygen from the atmosphere. And I know that because I noticed 13.66 milligrams gives us 10.71 milligrams and 3.28 milligrams. If you add these together, you get more than 13.66 milligrams. So that means that, excuse me, that means that some extra mass has come into play, and that comes in the form of molecular oxygen. I'm sure that what's going on here is we're burning our compound in oxygen, we're combusting it in oxygen, so we're going to get a little bit of extra mass from oxygen. So the mass of oxygen that we find here, right, we could find a mass percent of oxygen for this compound. The rest of this 0.0171 grams is made up of oxygen, but it doesn't really tell us anything yet because we're bringing extra oxygen in. Okay, so the next thing we want to do is find the mass percent of bromine in CHBRO. And for that, we're going to use this other piece of information. It says another 4.86 grams yielded 3.46 grams. So if I take 3.46 grams of Br divided by 4.86 grams of CHBRO times 100, that tells me that in this CHBRO sample, I have 71.2% by mass bromine. So let's move that up a little bit. So now I have all the information I need to find the mass percent of oxygen. So to find the mass percent of oxygen, well, 21.4 plus 2.7 plus 71.2, that's going to add up to some number that's a little bit less than 100. And whatever is remaining has to be made up of oxygen, right? This compound is made of carbon, hydrogen, bromine, and oxygen. And these are the percentages by mass. So whatever's left over, that should be the mass percent of oxygen. So if you basically just add these up and then subtract that from 100, the mass percent of oxygen must equal 4.7%. And I think if you take it out, it's 4.72%, but we can just round it there. I think that's good. So this is our mass percent of oxygen. Okay, so that's really the first part. It says calculate the mass percentages of carbon, blah, 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 blah. So now we're ready to solve for the empirical formula. And I think a lot of empirical formula problems, they start at this stage, right? You're told what the mass percents are. We assume 100 grams. We go through that. And I'll do that in a second. But getting to this point, this is really sort of what sets this empirical problem apart from all those other problems. we have to figure out what the mass percents are by doing this sort of combustion analysis and this mass percent analysis, which is definitely a little bit tricky. So hopefully that makes sense, how we went through that, and we'll go on to the next part. So the next part, I'm going to say, well, let's just assume 100 grams of sample. And I like to do it this way just because it makes these percentages, dealing with these percentages, a lot easier. And I think that this is sort of almost like a new problem. We can almost be thinking about this is step 2 of the problem, or part B of the problem. So if we have 100 grams of total sample, then that's going to take our percentages and just convert them directly into grams. So if I've got 100 grams total, it's 21.4% carbon, then that means it's 21.4 grams of carbon, and then 2.7 grams of hydrogen, and 71.2 grams of bromine, and 4.7 grams of oxygen. Now I'm going to convert all of these from grams into moles. So I'm going to show that calculation for carbon, and then we'll just do it, directly for everything else. 1 mole is 12.01 grams. So if you've got this number of grams of carbon, you should end up with 1.78 moles of carbon. We'll just sort of skip that step for the rest of these, and we'll say 2.66 moles of hydrogen, 0.891 moles of bromine, and 0.294 moles of oxygen. So again, just converting these grams into moles, using the molar masses for carbon, hydrogen, bromine, and oxygen. Now we've got a ratio, right? So now we've got sort of our mole to mole to mole ratio of carbon to hydrogen to bromine to oxygen. So there's lots of different ways to sort of go from here. The thing that I like to sort of the way that I'm teaching it currently, I guess is probably the best way to put it, is I'll say, well, these are our mole to mole ratios, right? 1.78 moles of carbon to every 2.66 moles of hydrogen to every 0.891 moles of bromine, so on and so forth. So I'm actually just going to write it like that. I'm going to say, well, these are the mole to mole ratios for carbon to hydrogen to bromine to oxygen. Now, we can't really have 0.78 of a carbon atom, so I'm going to divide all of these, divide by 0.294, divide by the smallest number, essentially. So if you divide all of these by the smallest number, then we're going to get whole number, or closer to whole number, hopefully, ratios. So if you do that, 1.78 divided by 0.294, you're actually going to end up with C6, H, again, 2.66 divided by this, H9, Br3, O1. And this is the empirical formula. So this worked out really nicely just when we simplified this, we divided by the smallest number, then this is the ratio that we get. It's a 6 to 9 to 3 to 1 ratio, which is actually the same as a 1.78 to 2.66 to 0.89. That ratio is the same between these and these, but we've just simplified it by dividing by the smallest number. So this is my empirical formula. So we're sort of checking off, so going way back up here, determine the empirical formula and the molecular formula. So we've got, and our mass percents. So we've got our mass percents, we've got our empirical formula. So now we want to figure out our molecular formula. So if you add up the mass of this whole thing, you end up with 336.85 grams per mole. So this is the sort of the empirical mass. The mass of C6H9Br3O1 is 336.85. So we want to compare that to our given molecular weight. Our given molecular weight is 673.72, which is about double. If you look at this number and you look at this number, you might say to yourself, well, that seems like it's about double. If you multiply this by 2, in fact, you end up with 673.7 grams per mole, which is essentially the same as 673.72 grams per mole. So what that tells us is that our molecular formula is just double our empirical formula. So our molecular formula should be C12H18 Br6O2. That is the final answer. So, like I said, this is a very involved, very difficult problem. It's got a lot of different steps. I think the trickiest part is probably this first part, figuring out what the different mass percents are. Figuring out what the mass of carbon is in this sample, relating that back to the mass percent in the entire sample. Obviously, this problem is more difficult because there was a typo in the original, so that's going to make it more difficult. Now, I did say at the beginning of the video that there's sort of a shortcut method. And the shortcut method involves taking this molecular weight and figuring out how many moles this is. So if you take this 0.01366 grams and you convert it to moles, and then you convert this number of grams into moles, then you can go directly to the molecular formula. You'll find that the ratio of carbon, the multimole ratio of carbon from this number of grams of carbon to this number of moles is 12:1. So it sort of directly goes right to the molecular formula. And then you could sort of back solve for everything else, but I don't think that that's the intention. So that's why I didn't talk about that. Okay, so that's it. Hopefully that helps. Let me know if you've got any questions. It's a long video.